Hello everyone. Today what we're going to do is begin the first of our video lectures. Now the reason we've moved from the Zoom classes to the video lecture is because of the nature of what we'll be studying. Management science is focused on, as we discussed, problem solving that eliminates bias and opinion from decision making. However, a lot of the methodologies are mathematics based, and not everyone has a strong background in that. It's also a very difficult topic to absorb if we're doing it through Zoom, because I can't check comprehension. Now videos make it almost impossible for me to check comprehension. However, what it does do is it allows, or it gives you the resource to go in and check the material again if you're unclear on what we've discussed, because the video is permanent. Through Zoom, that option isn't really available. So that's why we've moved to this new format. And most of our lessons, there might be one or two exceptions. If I feel like we have to revisit something in person, or we have a certain scenario, we may go back to Zoom temporarily. But it does look like this will be our predominant method of learning. So let's discuss this format. The first thing we're going to do is talk about attendance. Because this class is attendance based and there is no way to check if you're watching the videos, what we're going to do is, with each video that's uploaded, you will have a quiz to complete, and that will act as your attendance score. So for example, following this video, there will be a short quiz to complete. Your score on that quiz will dictate your attendance score. So for example, if you score 7 out of 10, over the course of the semester, your cumulative total on quiz scores will dictate your attendance. So for example, if your attendance score, average score over the course of the semester is 7 out of 10, your attendance will be 70% of the maximum. So please, the quizzes are critically important. Please take the time to complete them to the best of your ability. Also, each quiz or quizzes that are assigned are expected to be completed by the end of class time. If we have a 2-hour class beginning at 1 o'clock, so our class runs from 1 p.m. to 3 p.m. Because it's a 2-hour class, you'll have 2 videos to complete. Each video will be approximately 40 to 45 minutes. Once you complete the video, you will then be expected to go in and complete the quizzes. How to access the quizzes will be given to you in our Cacao group chat. But once you access the quiz, you have to complete both quizzes before 3 o'clock. Anything submitted after 3 o'clock will not be graded. It will be given as a 0 out of 10, and you will be assumed to have missed the class. You will have, if you are beginning the class, if you're beginning the videos at 1 p.m. when class begins, you will have no problem completing everything on time. However, in a scenario where you are not beginning at 1 o'clock, you may not have time. Please be aware of that. I cannot enforce a 1 o'clock start, but you should be beginning the tests at 1 p.m. As always, if you have any questions regarding our attendance policy or any other questions, feel free to contact me through Cacao. During our class time, the video will be uploaded, but I will always be available to answer any and all questions you may have about the material covered or anything I discuss in the video. So, if you have questions, again, please contact me. If not, let's move on. What we're going to do today is we're going to begin looking at linear programming problems. As we discussed, management science is about removing opinion and bias from decision making. It's about making optimal choices based on the mathematics guiding the information given to us. We are attempting to solve a problem to determine what the optimal solution is given the specific information from a given problem. There is no opinion, there is no bias, there is only the optimal solution as determined mathematically. So what we're going to do today is we're going to begin looking at linear programming. Now, linear programming is a methodology that is determined to make optimal choices, usually with maximization or minimization. For example, if we want to maximize profit, if we want to minimize labor usage, if we want to maximize products produced, if we want to minimize loss. These are all common situations where linear programming may very well help us determine optimal solutions. Now, another key point is with linear programming, these problems that we're working on have limitations or constraints. Constraint refers to, exactly as I just said, a limitation, something that limits your decision-making process. For example, you may have a limited number of labor hours. People cannot work infinitely. Instead, we have a certain number of labor hours to produce the products we want. That is a limitation. We cannot produce an infinite amount because we have a limitation placed on our decision-making process. That is an example of a constraint or limitation. Other constraints may be a required amount of vitamin A. We could be choosing between two vegetables. What is our optimal choice between carrots and broccoli? If we require X amount of vitamin A, given the vitamin A in carrots, given the vitamin B in broccoli, how do we choose the optimal choice knowing we have a constraint or limitation of 10 grams of vitamin A necessary? Linear programming helps us solve problems of this nature. This is the type of thing that we're going to be reviewing as we move through the next section of this course. So, essentially, when we begin a linear programming problem, we have 3 steps to follow, 3 basic steps. Number 1, we have to determine, does it have the proper characteristics of a linear programming problem? For example, does it have decision variables? Does it have choices to make? For example, how many sofas or how many chairs to produce, how much broccoli, how many carrots, how many pizzas, how much chicken. We have to have decision variables that we are attempting to decide. We also need to be able to relate those variables to each other. We have to be able to find a connection between them so we can choose between those two things. Finally, we have to have constraints or limitations. If we don't have constraints, the options will be none or infinite. However, in the real world, we always have limitations governing our choices. So if the problem has limitations, if it has decision variables, if those decision variables can be related to each other, then we can follow a linear programming format to solve the problem accordingly. We're going to be doing that using algebraic principles, but for the first section, what we're going to be focusing on for now isn't going to be problem solving, but problem or model formulation. We have to take the natural language problems that we're given, and we have to write them in a format that can then be used, where we can then use algebraic principles to solve those problems. So what we're going to do now is we're going to look at several examples. When we do this, I will no longer be on the screen because what we'll be doing is we'll be looking at my computer screen and we'll be using those principles. I'll be speaking while solving, but I'll be taking you through several example problems. When I go through those problems, you'll be following along as I explain the thought process and as I explain the methodology while we move through those problems. So, thank you very much, everyone. This is the completion of section A of video 1. We'll resume in a very short time, but when we resume, it will not be with me on the screen. It will be following the problem-solving methodology as I work through problems with you. Thank you for listening to section 1. See you shortly. Hello, everyone, and welcome back. As I said before, what we're going to be doing now is recording this video, but instead of me explaining to you and you having to picture the images, what we're going to do is we're going to work through problems together while looking at my screen. Often we'll be looking at the full screen as we are now, but I have left several blanks in my PPT because we will be filling in some of the key information together. This idea, linear programming, as I said, is immensely useful in real life. It allows us, when we're limited, to make optimal choices based on the information given to us. However, and something to remember is that a lot of the problems we see now at this base level are not overly realistic in terms of real life, only because we've simplified everything to a huge degree so that learners like you who are just beginning to look at these concepts can follow the information being given to them. In real life, the problems are obviously exponentially more complex, but generally follow the same principles that we'll be discussing here. So let's get started. And what we're going to be doing today is working through first one problem in great detail, and then continuing on with a little less detail, so hopefully you can follow along and shortly be able to complete similar analyses by yourselves. So let's begin. The first step when we're doing problems of this nature is we have to identify key points. We have to check if the problem has the ingredients necessary for us to solve it in a linear programming fashion. First up, we have to identify whether it has decision variables. Now, what I mean by decision variables is, are choices being made? When we first begin, we're going to see that we're typically going to stick to two decision variable questions, meaning we're going to be working with questions that focus on two choices, choice A, choice B, or a mix of A and B. However, in the future, in both this class and the follow-up managerial decision making that you'll take in the future, we will get to questions with multiple decision variables, 2, 3, 4, 15 different decision variables. But for now, the key point is determining, does the problem that we're looking at have decision variables? Are we making a choice between A, B, or a combination of A and B? or when solving these problems, we're going to generally label our decision variables x1, x2, x3, etc. When you were younger and looking at algebraic problems, your instructor may have labeled them x, y, z, etc. That is also possible. But we're going to not do that this time. We're going to stick with x1 and x2, x3, etc. Because as we get to more complex problems, if we have 4 decision variables, 5 decision variables, 8 or 10 decision variables, choosing a different letter of the alphabet, the Roman alphabet, for every decision-making variable becomes much more complex. So for now, we have to identify decision variables, and we're going to label them x1, x2, x3, etc. Next, we have to check that we can relate those decision variables to each other in an objective function. This is a complex way of saying, can we relate A and B, for now, A and B, to each other? Are we able to draw or find a relationship between them? So is it A, is it B, or is it a combination of A and B? Is it x1, is it x2, or is it a combination of x1 and x2? We have to be able to relate these decision variables to each other. And finally, step 3, we have to check if we can solve this problem or solve these problems using algebraic principles. We have to check if we are able to manipulate, using algebraic principles, the terms given to us to solve for our unknown variables. So these are the basic key points when we investigate any problem. However, and this is key, for now, the identification of key points, that's a real life issue. If we have a problem in real life, we have to check, can I apply linear programming principles to this real life problem? If we're wondering, that's where we have to check these key points. Because this is a management science class, all of the problems given to you will be linear programming problems. We don't have to worry about identifying these key points. But in a real life scenario, yes, you would have to consider these ideas. Let's move on. I'm going to present you now with this very basic but illuminating practice question that will allow us to look at some of the topics we've discussed so far. This question will allow us to go in and check, or to work through together and highlight the key information to hopefully begin to show you how these problems work in a real life scenario. So step 1, let's review this question. The Beaver Creek Pottery Company is a small crafts company operation run by a Native American tribal council. The company employs skilled artisans to produce clay bowls and mugs with authentic Native American designs and colors. The 2 primary resources used by the company are special pottery clay and skilled labor. Given these limited resources, the company desires to know how many bowls and mugs to produce each day in order to maximize profit. So let's go back to what we just discussed. Does it have decision variables? We see here they manufacture two products, clay bowls and mugs. So we're choosing between bowls and mugs. Now we have decision variables we can solve. Can we relate those decision variables to each other? Yes, we will see that those, because there's a direct correlation, we can produce one, we can produce the other, or we can produce a combination. We know that they are related to each other. And can we solve using algebraic principles? Yes, you will see that we can. So our conclusion in step 1 is that yes, this problem is possible to solve using linear programming principles. Let's continue on. So here we see the key points. Clay bowls and mugs. Those become our decision variables. Two primary resources, special pottery clay and skilled labor. If we recall, problems like this, we solve by, or we are looking for optimal solutions if limitations are present. We see here they have two key resources. And a key point is that resources are not unlimited. Resources are limited. This is the real world, where we have limitations on how much we can use resources. Look at this situation, skilled labor. If we want skilled labor, we have to pay for it. We cannot have infinite labor. We can hire more people, and more people can work longer hours, but no one is able to work an infinite number of hours. So, by definition, this is a limited resource. We also see special pottery clay right here. This too, by definition, has to be limited. We cannot produce an infinite number of clay from the ground. Where they find it, how they produce it, all of this means there are finite limits to how much we can produce. So we see that we have limited skilled labor and limited pottery clay. So now we see that from our limitations, with what we have available, now we're trying to determine the perfect solution. Now we're trying to determine how we can find the perfect mix of bowls and mugs that will give us what we want. And what do we want? It's highlighted here in the last sentence. We want to know how many bowls and mugs are we going to produce each day so that we can maximize profit. As I said earlier, typically these problems are based on maximizing or minimizing something. We want to maximize our profit. We want to minimize our loss. We want to maximize our revenue. We want to minimize our cost. We may want to maximize our vitamin intake. We want to minimize our labor costs. What we're doing is looking for perfect solutions given limited resources when trying to maximize or minimize something. That's essentially what we're doing. So we're looking at this native or natural language problem. This is written to us in natural language. But what we have to do is we have to translate that natural language into a mathematical format. Only when it's in a mathematical format are we able to properly solve the problem using algebraic principles. Now, we're not going to be solving yet. For now, we want to focus not on solving problems, but instead we're focusing on the translation of natural language to mathematical format. So let's continue. We have decision variables. The first step is highlighting our decision variables. Clay bowls and mugs. How many bowls and mugs to produce each day? So, as we recall from what I said just a little while ago, we want to assign variables for each of our decision variables. In this situation, we have two variables. Clay bowls is one, mugs is the other. Now we have to assign variables to those. So in this case, and as we said earlier, we're going to use x1, x2, etc. So in this situation, clay bowls will be x1, where x1 represents the number of bowls we will produce. Mugs will be x2. x2 represents the number of mugs we will produce. So we have clay bowls, x1, and mugs, x2. We've now identified our decision variables. Now, the next step is we have to determine, are we trying to minimize or maximize in this situation? The question will always tell you if we're trying to minimize or if we're trying to maximize. As I said before, we can maximize a variety of things. We can minimize a variety of things. But in this situation, and with these limited resources, the company wants to know how many bowls and how many mugs to produce each day to maximize profit. That's the key point here. So we have x1 is how many bowls, x2 is how many mugs, and we want to know how many bowls and how many mugs to produce to maximize profit. The third step is that we have constraints. And this is a concept we're going to see again and again and again. Constraints are the limitations placed on the decision-making process. If I ask you, if I say, I want you to maximize profit, how many bowls will you produce? The answer will always be an infinite number. More bowls, more money, more profit. But in real life, we cannot produce an infinite amount because we have constraints, limitations, or guidelines. All are the same thing. These are the ideas or the resources or the rules given to us that limit the choices we can make. In this situation, we cannot produce unlimited bowls and mugs because we have two constraints. We have limited special pottery clay and we have limited skilled labor. those two limitations, they govern the choices we can make. And again and again and again, with every problem you see like this, you will have constraints governing your decisions. At first, and with these simple questions, we're going to have 2 constraints per problem. But very quickly, we'll introduce additional constraints. Now, constraints can be anything, but they are things that limit your decision-making process. They are those ideas that tell us how much we can make, how much we have to buy, what is the ratio from one to the other, what times are available, how much storage space is available, etc. So in this situation, we have 2 constraints. 1, limited pottery clay, and 2, limited skilled labor. Let's move on to the specific information now. So the Beaver Creek Pottery Company is a small crafts company operation run by a Native American tribal council. The company employs skilled artisans to produce clay bowls and mugs with authentic Native American designs and colors. The 2 primary resources used by the company are special pottery clay and skilled labor. Given these limited resources, the company desires to know how many bowls and mugs to produce each day in order to maximize profit. This information we've seen already, but we don't yet have the parameters. And the parameters are the specific numbers associated with, in this case, the manufacturing process. These are the numbers that will enable us to solve through algebraic principles the question that we are considering. So let's look at the specific numbers. We see the 2 products have the following resource requirements for production and profit produced per item sold. We see here 1 bowl takes 1 hour of labor and 4 units of clay, and it produces a profit of $40. 1 bowl takes 2 units of labor and 3 units of clay, and it produces a profit of $50 per item sold. So we see here, finally, that there are 40 hours of labor. So bowls are 1 hour, mugs are 2 hours, and we have a total of 40 hours available. We see bowls are 4 units of clay, mugs are 3 units of clay, and we have 120 units of clay available. Now, given all of this information, we can now begin to solve the problem given to us. Now we can take this natural language information that we've been given, and we can translate it into the mathematical formula we require, the model formulation necessary to solve this problem algebraically. So let's do that together. Here, we're going to go back into my template because I haven't yet written the key information because I want to do it together. So we see here the Beaver Creek Company and etc., etc. We've seen this again and again. Going back to what we discussed earlier, step 1 is writing the decision variables. And as I said before, we're going to go with the x1, x2, x3, etc. format because it allows us to see, or it allows us to continue using the same format no matter how many decision variables we have. So x1, as we said earlier, is the first choice among many that we're making. In this case, x1 represents clay bowls. x2 represents mugs. Those are the two choices we're making in this situation, and we can see that right here. How many bowls, x1, how many mugs, x2, will we be producing? x1 will represent the number of bowls. Let's write that in here just for ease. Number of bowls, of clay bowls, the number of clay bowls that we will manufacture. And x2, again, is similar. It is the number of bowls, number of mugs that we will manufacture. That is what x2 and x1 represent. The next step is relating the decision variables with the objective function. You'll hear the term objective function again and again and again. And what this represents is how we're going to connect these two ideas together. How we're going to find, or how we're going to see these, or how we're going to connect these two ideas. So in this situation, we know we're trying to maximize. We know we're trying to find a situation where we want to know how many of each to produce in order to maximize our profit. So let's look at that together shortly. We're trying to maximize Z. And Z in this situation represents profit. Z is the money that we are going to make. So we're trying to maximize our profit given the number of clay bowls and the number of mugs that we will manufacture. So to do that, we have to enter how much money we will make per unit to complete the process. So we're trying to maximize our profit given 40 x1 plus 50 x2. That means we're trying to maximize our profit given $40 per bowl manufactured plus $50 per mug manufactured. That information we found right here. The final step is we have to write the constraints. C1, first constraint or first limitation, and C2, second constraint or second limitation. Our first constraint is limited labor hours. Let's do limited labor. So we know it's 1 unit per bowl, which is x1, plus 2 hours per mug, which is x2, and we have less than or equal to 40 hours available. So here we see we have 1 hour for every bowl, x1, 2 hours for every mug, x2, and that must be less than or equal to 40 because that's how many hours of labor we have available. That's what we've done here. We repeat this process one more time. We see for every bowl it's 4 units of clay. So 4x1 plus, and we see here 3 units for mugs, 3x2 less than or equal to 120. We can use less than 40, less than 120. We can use 40 or 120, but we cannot use more than 40, more than 120. That's what we've represented here. And that is pounds of clay available. So we've completed our 3 steps here. We've written the decision variables, x1 and x2, which is how many bowls, how many mugs we'll manufacture. We've related them through our objective function, 40x1 plus 50x2. And we've written the constraints, which are 40 hours of labor and how much labor per bowl, how much labor per mug, and how much clay is available. 4 units of clay per bowl, 3 units of clay per mug. So what we've done is we've taken the natural language question and we've written it in a format that will allow us to solve it. What we've done here is we've simply collected all of the information together. Our final solution has the information collected together in one space. We're trying to maximize z equal to 40x1 plus 50x2, given the subject to, according to, our first limitation, 1x1 plus 2x2 is less than or equal to 40, and our second limitation, 4x1 plus 3x2 is less than or equal to 120. This is our final problem formulation. From here, using algebraic principles, we can then begin solving the equation. We're not going to do that yet. We're focused on problem formulation. But this is a basic idea of how we can formulate problems of this nature. Hopefully everybody's clear. That's it for right now. That's the end of our first video lecture. Thank you very much for listening. I hope everyone followed along carefully. Please complete your quiz as soon as possible.